Hey friends, welcome to Chemistry Lover, and in this video I am going to discuss about the ring opening reaction, or the epoxide ring opening reaction, and when the epoxide is part of the cyclohexane ring system. So normally in normal epoxide ring opening there is not much stereochemistry or regiochemistry involved, but when you talk about cyclic epoxide or the epoxide which is a part of the cyclohexane ring, its stereochemistry is very important. And in this case I took this particular example from csir-net exam, which is a 4-marker question. You can see this is just a one-step reaction. What will be the product on reaction of this thiophenoxide anion with this epoxide? So you have to just tell that and you will get 4 marks. But for this question to attempt, or for this question to solve, you have to know what are the factors that determine the regioselectivity or the stereoselectivity in epoxide ring opening when it is a part of a cyclohexane ring. Okay, and I also took this another 2 questions which involves the same concept, and I will discuss about what other questions are possible from this particular topic, right? So when we talk about this particular question, this question number 1, so here first we have to draw this bicyclic ring system, or it is actually a tricyclic ring system, but the main part of this molecule is decane, right? So we have to draw it in its proper conformation and configuration, and that will be like this. So you can see 2 cyclohexane rings are there, and we can represent it like this. Now we can put the methyl group above the plane and hydrogen is below the plane. Now why we are writing this trans stereochemistry? Because you can see this hydrogen is below the plane and methyl is above the plane, so it implies that it is in trans configuration. And if it is in trans configuration, you have to put these 2 groups axial, because if you put the other ring C bond in axial position, then you cannot form the ring, right? So in the trans system, always you have to put the other substituents axial. So this will be the proper configuration. Now you have to put this epoxide ring. So you can see both this epoxide and this methyl, they are above the plane. So it will look like this. So it will look like this. You can see it implies that this epoxide is above the plane. Okay, and now the question is whether your so in this case the nucleophile is this SPH minus, so whether it will attack from here or it will attack from here, that is the main question, right? So now let's see what are the products if this SPH attacks from this side, or if this SPH attacks from the other side. Okay, so in this trans-decalin system, either your SPH can attack on this particular carbon or it can attack on this particular carbon. So let us first see, when the attack is taking place on this particular carbon atom, what will be the product. So in this case the product will be like this. So here you have the methyl group, here you have the hydrogen, and your SPH is attacking here. So your OH will go here, because you can see this oxygen is above the plane, right? So the attack has to be from below the plane. So your SPH is attacking from here and it is coming above the plane. So your OH and your methyl both are above the plane. So if we draw this product in our flat configuration, what will be the product? So here you have the methyl group, here you have the hydrogen, and you can see the OH and methyl are on the same side. So OH will be here and your SPH will be here, right? So this can be one product. What is the other possibility? So other possibility is that this SPH group can also attack on this particular carbon, right? Actually the attack is from below the plane. So now what will be the product? Now you can see if the attack takes place on this particular carbon, that product, the initial product which will be formed, that is actually in the both configuration, but we can flip it and we can draw the chair configuration of the product. So the chair configuration of the product will look like this. SPH will be here and your OH will be here, right? But you should understand that in one state this product is not possible. So basically the product should be obtained here is your methyl group is again above the plane, but in this case the SPH is attacking from the other carbon atom and it is also below the plane, and this OH is here and this hydrogen is here. Now the four options which were given, these two were there and other two options were there where your OH may be below the plane or SPH above the plane, like that. But these options were there. Now you have to select which is the correct answer. So you can see this will be the correct answer. Why? Because this product is perfectly right, but this product cannot be obtained in a single step. First, what will happen? You should note that first. So we will consider only this part, right? So we just ignore this particular cyclohexane ring. We consider only this part. So we can write down this like this. Okay, so this is how a cyclohexane epoxide looks like. It actually doesn't look like a chair form, but the four carbon atoms which are adjacent to this epoxide, they are actually in the same plane. So it basically looks like this. Now we are talking about two different mode of attacks, right? So either the nucleophile can attack here or the nucleophile can attack here. Okay, so now let's say the nucleophile is attacking on this particular carbon atom. So then what will be your product? So then this will be your product, right? Now if the nucleophile attacks on this particular carbon atom, what will be your product? So in this case you will get a product like this. So you can see basically your nucleophile is here and your OH is here. Okay, so after flipping, it is different aspect that after flipping you will get the chair form like this. So basically you will get your OH here and your nucleophile here, but that doesn't matter because the transition state looks like a boat form. When the attack is taking place on this particular carbon atom, the transition state which is involved, that actually adopts the boat form. So you know the boat form is energetically less favorable than chair form. So the molecule will always try to minimize its energy in the transition state, and that's why it will choose a pathway when it will go through a chair-like transition state, and you will get this process. Same logic if you apply in this particular example, you can see that this product will be obtained when it goes through a boat-like transition state. So that's why this pathway will not be followed, and it will undergo the other way attack, and that will give you this product. So this will be your correct answer. Now let us look the other two questions which are given here. Okay, so these two questions are given. So again we have to first draw them in proper way. So we can draw it like this. So here we have this nitrogen. Okay, so this NH group is here. Now this phenyl group, if we place it in the pseudo-equatorial position, then you can see the phenyl and this epoxide, they are anti to one another. So phenyl is directing above the plane, so this epoxide will be below the plane. Okay, now we have to decide which corner will undergo the attack, right? So either the nucleophile, in this case azide, it can attack here or it can attack here. So basically if the nucleophile attack on this particular atom, what you will get? You will get this product where you have this N3 here, this NH here, and this OH here, and also this phenyl here, right? So this can be your product. Or if so this is the product when your epoxide azide is attacking here, but when your azide attacks here, what will be your product? So in this case your product will be a boat form, right? So here you have N3, here you have OH, here you have this NH, and here you have pH. So obviously it will not follow this pathway, so you will get this product here. But in this particular case the configuration is slightly different, right? So in this case if you draw it, what you will see, you will see that, so if you place this phenyl here, you can see in this case both the phenyl and this oxygen, they are on the same side. So phenyl is directing upward, so your epoxide should also direct upward. So in this case one thing I should mention is that although this dotted bond represent it is below the plane, and this bold bond it represents is above the plane, but we don't have to care about whether we put it below or above. We just have to maintain the cis-trans relationship. So one is bold and another one is dotted, that means they are trans. In this case both are dotted, that means both are cis. So we don't have to put this phenyl below the plane, we can put it above the plane, but we have to place then this epoxide also above the plane because they have the cis relationship. So now you can see in this particular case, if attack takes place on this particular carbon atom, you will get the chair form product. So here you have the phenyl, here you have the NH, and basically the epoxide is here. So you are getting this N3 here. So these give you the cis product, sorry, the chair form product. Whereas if the attack takes place on the other carbon atom, like this N3, and here you have OH, then you would get the boat-like transition state and boat-like product. So that will not be the case. So in this particular case you will get this product, and in this particular case you will get this product. So now you can also write down the same product in the flat configuration like this. So in this case what you have to draw, so the same thing. So basically you can see this, so here you have the NH and here you have the pH. Now the pH, in this case the pH and the OH, they have the trans relationship. So that means your OH will be above the plane and your N3 will be below the plane. So you can see N3 and the phenyl has the same side relationship. So in this case also the N3 and the phenyl is on the same side. So that's how you have to convert it from here to here. So the main point which you should remember while writing this reaction is that always you should attack on that particular carbon atom which give you the chair-like transition state and chair product in the first step. You don't have to attack where you will get the boat product. Steric hindrance factor has no effect in this particular way. That means in this case you can see although the phenyl group is on above the plane, that doesn't mean that your nucleophile will not attack from above the plane. It is attacking from above the plane. So steric hindrance has no importance. The stereoelectronic factor is more important, that the stabilization of the transition state. So in this case you can see, in this case the attack is occurring from the other side of the phenyl group. So you can see that phenyl group is above the plane, but the attack is occurring from below the plane. So one can ascribe it like that due to the steric hindrance of this phenyl group. That's why it is attacking from below the plane. But that doesn't matter. Steric hindrance doesn't matter. The only thing which matters is the stereoelectronic effect and the stabilization of the transition state. So always this type of reaction will follow the pathway which give the chair-like transition state, and the same logic is applied when you add some reagent across the double bond, that is cyclohexane ring system, and I discussed in details the case of cyclohexane ring system in my other video. You can watch that video, the link is in the description section. So that's all, and I hope I'm able to make you understand the concept. So if you like this video, then share this video with your friends, and if you're new in this channel, then subscribe my channel, and thank you for watching.